we can move to another talk, to the third talk of the second day with Pamela Harris from Williams College. The title of the talk is Parking Functions and Combinatorial Games. If Tofik has already given host to Pamela, she can probably begin.
Okay, can everybody see my slides okay?
Yes.
Awesome. All right, I'm just going to move the screen with the videos. All right. Well, thank you so much for the invitation. I'm super excited to be here and just have this opportunity to share with you some of the work that I've been doing with a lot of students, undergraduates and graduate students, and some other collaborators. And so I'm just going to start with some basics. So what is a parking function? Oh, it looks like something's getting cut off there. Okay. So what is a parking function? So it's this scenario. So imagine that you are having a queue of cars. So you have car 1 all the way to car n entering a one-way street with parking spots numbered 1 through n. So the same number of cars as the same number of spots. What we're going to do is each car is going to enter the street having a preferred parking spot, and they're going to go to that parking spot. If it happens to be empty, then they'll park there. Otherwise, they'll just continue down the one-way street trying to find the very first available parking spot. And so the trick is, if I give you all of the preferences for the cars, my question to you is then, can all the cars park? And if so, then we'll say that the list of the preferences for the cars is what we call a parking function. So here's an example. So I keep track of the index. So this is the first entry in the vector. That's just the preference for car 1. The second is the preference for car 2, and the third, the preference for car 3. So in this scenario, car 1 enters the street, finds its preferred spot available, it takes it. Car 2 enters the street, but finds car 1 parked there. So it just continues down the street and parks in the second spot. Car 3 enters the street, finds its preferred spot available, parks there. And so, yay, we have this parking function. But of course, not every preference list is a parking function. Take, for example, 313. So car 1 enters the street, parks in its preference, spot 3. Car 2 enters the street with a preference for spot 1, parks there because it's available. And then the car 3, unfortunately, finds its preferred spot occupied by car 1, so it is unable to park. And so this preference list, 313, is not a parking function. Now, of course, playing that little combinatorial game is not that hard if you don't have that many cars. But if you have a much longer set of cars, this is harder to do. And so luckily for us, there's a nice characterization of parking functions. So what you can do is you rearrange the parking preference list in non-decreasing order. And then you just ask yourself, is the ith entry less than or equal to I? And so for these two examples that I have at the top, I just did exactly that. So on the left-hand column, I have the numbers that are in the list, just rearranged. And then on the right-hand side, I just have the number I. And so in this case, you notice that all those inequalities are satisfied. And so that is a parking function. However, immediately that checking this list violates these first two inequalities. And again, you only need one to not work for the whole thing to not be a parking function. So great. So now you have a way to characterize. And of course, then you might ask, well, how many of these objects are there out of the n to the n preference list that we could have? And so there's a beautiful proof by Pollock that consists of 6 sentences. And I should tell you, I've read it a few times and I always get a little confused. And so I worked with a student at Williams College, Kimberly Hadaway, who will make an appearance later as well in the talk. And we worked on this article. And so in case you're interested, we just put a little bit more detail into that work. Now, let me shift gears a little bit and think about a parking function statistic. So in this case, what I'm going to think about is the displacement, meaning what happens to the cars when they find their preferred spot occupied? Well, they get displaced from that preference by some amount. And so let's keep track of that. So I'm going to take D of alpha to just be the sum of Ki from 1 to n, where Ki denotes the displacement from where car I wanted to park to where it actually parked under that preference list. So for example, if it happens that alpha is a permutation, well, then there's no displacement. Every single car gets exactly what they want. Now, in all other cases, there is some displacement that occurs. So D will be positive. And in fact, if you have that alpha is just the preference list where every single car prefers the first parking spot, then of course you take the sum from 1 to n and you get n times n minus 1 over 2 as the displacement. So here's one interesting thing that came up when we were looking at displacement. So this is titled On Parking Functions in the Tower of Hanoi. And this was work that we undertook with some undergraduates at Williams College, and then also a group of research students at MSRI up in 2021. So this is soon to appear in the Mathematical Monthly. So consider this game, and then I'll show you how they're related to displacement. So we're going to think about the Tower of Hanoi game. Now, the starting position for the Tower of Hanoi is that you have these disks arranged in increasing order from bottom to top, decreasing order, they're getting smaller at the top. And your goal is to move the disks among the pegs to get them from what we call the source, so here's the source peg, to the terminal peg or ending peg, by being able to just move a disk at a time, and you never are able to stack a big disk on top of a small disk. So those are your rules. So let me tell you about something that was studied in studying the Tower of Hanoi game. So it's called an ideal state. So this is simply a rearrangement of the disks, in this particular case, n+1 disks, having the following properties. So the first thing is that you're going to label the disks, the largest with the label n, to the smallest, the largest disk, labeled n. It happens that that one just remains on the original source peg. So that's how this ideal state is defined. And then you're going to have in the destination peg, everything the destination peg labeled n, so that's the very last one, is the only empty peg. And what happens is the remaining n disks happen to be in the interior. So basically not in the source and not in the final peg. They're all in the middle. And they're arranged in such a way that each interior peg has at least one disk. Well, then that means that there's exactly one of the pegs having 2 disks. So the main result is that if you consider these particular ideal states and you look at the parking functions that have displacement exactly 1, they're actually in bijection. So these are the same thing combinatorially speaking. So one of the things that we don't know, let me tell you about these law numbers. So they're enumerated by the law numbers, which are given by this formula here. And the thing that's really interesting is that, so we ran some data, but we couldn't find any other connections. If you let displacement be larger than 1, we couldn't find any other types of ideal states in the sense of the definition I gave just previously to the Tower of Hanoi between these 2 sets. And so there's some open problems remaining in that particular paper. So if this is of interest, please check that out. And the Math Monthly does a double anonymous referee process, but we did, after the paper got accepted, we did put a copy on archive, which is pretty true to the final version. So please check that out. Now, let me tell you another story about parking functions. So here's Allison. So Allison worked with Katie Johnson at Florida Gulf Coast University. And as part of their program, as undergraduates in mathematics, they developed some research questions, and from which then they pick a project that they're going to do as an undergraduate thesis. And so Allison asked, well, what happens if a car, when going to its preferred spot, finds it occupied, and instead of considering just going forward in the street, they decide to check to see if the spot behind their preference was occupied? If that's the case, how many such things satisfy this new parking rule? And so you can start thinking about the fact that if you can actually park without ever needing to back up, then you should be able to park if you can back up. And so there's got to be more of these, what she called Naples parking functions, than there are parking functions. And in fact, not every Naples parking function is a parking function. Let me recall this example that we considered earlier. So 313. So that vector we know does not allow the cars to park under the classical parking rule. But now we just need to check whether if we allow the car to back up, then we'll be able to actually park. So here's the Naples parking version of this. So the first thing is car 1 enters the street, wants the 3rd spot. There it is. It takes it. Second car enters the street, wants the 1st spot. It takes it. And then at the end, what normally would go wrong with the classical parking functions, which is it goes to this spot and now just continues forward, well, now it can back up into the spot previous. And so there is a Naples parking function, which is not a classical parking function. Oh, and I see in the chat, Thomas, parking functions are in bijection with critical configurations of the chip firing game on complete graphs. And in this, the displacement maps, I think, to the well-known level statistic. Oh yeah, cool. So yeah, there's definitely some really fun bijections and lots of connections. Thank you for that. So the research question that Allison pondered then is, now that we know this definition of Naples parking functions, how many such lists are there? And so I thought, Allison, if you're not going to work on this, can my students work on it? And so she worked on a different problem and my students worked on this. So in 2019, our group of students at MSRI took on this challenge. And in fact, they did a little bit better. What they did is they generalized further. They said, well, why only back up a single spot? What if we back up to K? And so that's how they defined this. They introduced a new parameter K, and that was a parameter that allowed the cars to check up to K spots behind their preference when finding that occupied. So again, the parking rule in this setting, each car, as always, tries to park in its preferred spot. If it happens to be occupied, it will check up to K spots behind its preference and park in the very first available one. So you just check one at a time. You don't kind of zoom all the way back and then go forward. Now, if all K spaces are occupied or you run to the front of the street, then and only then do you consider going forward in the street parking in the very first available. And then if all cars can park, that's when we call this a K-Naples parking function. And so our main result gave a enumeration for these using a recurrence. And there's so many open problems remaining in that paper. So this one got published in the Electronic Journal of Combinatorics. So, but I would say that there has been some progress made in some of the open problems that we listed in that paper. So you should check the archive for updates before you undertake any of those listed there. Now, let me tell you another problem that we've been thinking about. This one's called interval parking functions. So in this case, we're going to have n parking spots and n cars, again, on a one-way street, but now cars only want to park in a particular interval of spots. And so here's the definition. So now I'm going to tell you where they want to start parking and basically what they tolerate. How far out can they go to decide whether they can park or not? So here's an example. Oh, and of course, if they can park within that little interval that they prefer, if every car parks in their preferred interval, then we'll call this an interval parking function. So here's one preference vector. So in these cases, the preference vectors, again, have a sort of the start of what they prefer and then also the tolerance. So 1, 1, 1, 3, 3, 3, this one works because the car prefers to start at spot 1, and then it tolerates going to the end of the street. And so in this case, if you park the cars, they park in the order 1, 2, 3, they all fall within the interval. However, if you look at this one, what happens in this case, car 2 prefers spot 2 initially, and it parks there because it's the first car. Car 2 enters the street wanting to also park in that spot. And in fact, it only tolerates that spot, but car 1 already took it. So in fact, this is not an interval parking function. Now, it was already known, so there was a group of students out of the graduate research workshop in combinatorics who worked on this problem, and they enumerated the number of interval parking functions of length n with this formula. And so the way that they did that is they said, well, consider a parking function. If all the cars park, then you know that in spot I, somebody must have had the preference for spot either I plus 1, all the way to n. So there are this many options for each of the betas for each of the parking functions. And so then you take the prop. And so that gives you a way to characterize and really count all of the elements in these interval parking functions. So one of the things that my students and I were working on were these interval parking functions. So instead of just letting all the cars have sort of varying intervals that they want to park in, we actually just specify an interval of length. So in this case, we give you a non-negative integer L, and we say we start with a parking function. In this particular case, we generalize to having m spots and n cars. So there might be more parking spots than cars. And then we'll say that alpha is an interval parking function, and if each car can park in its preferred spot or in one of the next L spots following. And so this is where we started working with MSRI Up 2021 group of students, along with Kimberly Hadaway, who studied the L equals 1 case, which I'll show you some results about shortly, because we were able to count these, but the formula was terrible. It was just awful. And so I said, I know, it's not pretty, but let me show you the L equals 1 case. So here's a brief detour into something that Kimberly rightly named Fubini rankings. So a Fubini ranking considers a competition with n players, and they each get a rank. So you imagine that, you have 3 people, and usually if you see the Olympics, although there's some debate, anyways, what happens if you have 2 people that tie for first? Well, they kind of take spot 1 and 2. And so then the next available rank that would be allowed in that competition would be 3. So that's basically what Fubini rankings are. It's the set of all Fubini rankings on n competitors. So ties are allowed, but then they cover certain of the ranks. So for example, if we look at the Fubini ranking 1, 5, 2, 2, 4, you can imagine how the players are ranked. So in first place is competitor 1. In second place, you see competitor 2 and competitor 3. In third place, there's no one there because competitor 3 and 4 basically cover those 2 ranks. And then you look at fourth place, that's competitor 5. And then competitor at fifth place was the second competitor. And so this is a Fubini ranking. Now, enumerating the unit interval parking function, so again, that's the L1 case, gives you that specialization to that nasty recurrence formula that I showed you, but in fact, it's really beautiful. So the first thing to note is that the set of unit interval parking functions of length n is actually in bijection with the Fubini rankings with n competitors. And so from that, we're able to use this known result, which is that the number of interval parking functions is given by the Fubini numbers or the ordered Bell numbers. And so here's some initial terms. So really, really nice result once you when you specialize to L equals 1. All right, now let me tell you this other game we played. So Brian was a student in one of my classes at Williams, and he said, oh, this is interesting. I like these parking function things. But there are times where, in real life, somebody is more valuable player than another. And so what happens in the case where maybe somebody gets bumped out of the spot that they prefer? And so he considered this definition. Suppose a car J enters the street and, as always, proceeds to its preferred spot, P sub J. Of course, if available, you'll park there. However, if it happens to be occupied, that means that a car earlier in the queue took your preferred spot. In the MVP parking function, what we're going to do is we're going to take car J, it's going to bump whatever car was in its preferred spot, and then car I proceeds down the street to find the next available parking spot, of course, if one is available. And so notice that the bumping of cars does not propagate. So it doesn't mean that car I now gets to bump another car out of its preferred spot. It only happens once. And so, for example, let's look at 1111. That happens to be an MVP parking function, but notice what happens. Car 1 enters the street and parks in spot 1. Car 2 enters the street and bumps car 1 out of its preferred spot, and now car 1 parks in spot 2. Car 3 enters the street, bumps car 2 out of the preferred spot, and then car 2 parks in spot 3. Car 4 enters and bumps car 3 out of its preferred spot, and then car 3 proceeds all the way to the end of the street, parking in the fourth spot. So car 1, 2, 3, and 4 park in the order 4, 1, 2, 3, respectively. Okay, so some initial results. If I let MVP sub n denote the set of all MVP parking functions of length n, these things are in bijection. So there's the same number. And in fact, not only are they in bijection, they're literally the same set. So it's even better than that. And of course, this holds why? Because as long as the cars can park, it doesn't really matter which car took what spot, at least if that's all you care about, that if they park and not really caring about the order in which they park, which you'll see what happens soon. So we started thinking about that. How is that order changing? Can we talk about the way in which a preference will force cars to park in a particular order? So here's where the outcome map shows up. So suppose that I have this map. So I'm going to use the script O, P, F, N. So that takes me from parking functions into permutations. And the way that that works is it just literally tells me where car I parks using the classical parking process. And then I do the same thing, but for the MVP parking process. So again, this B sub I is just going to be where car I parks under each of those respective parking processes. So here's one question that was already studied. So if I look at a fixed permutation, so I tell you the way the order in which the cars park, I want to enumerate the parking preference lists, which ensure that the cars parked in that order. And so here's the result. You can do it by looking at products of some longest subsequences of the permutation satisfying certain properties. And in fact, we generalized, and I wanted to point that this result showed up, or this set of results showed up in the Enumerative Combinatorics and Applications Journal. And so we did this kind of result, but for the K-Naples version. And so having had that experience, we thought, well, what happens if we look at the MVP rule? Well, in this case, it got a little bit more challenging. So let me tell you this story. But our problem was the same. So fix a permutation, meaning the order in which the cars park, and then enumerate the lists of preferences that park the cars in that order. And so the first thing that I need to do is give you, some scary slide, but let me just tell you really what this set does. So pi is the order in which the cars park. So take, for example, this permutation. And then I look at the cars that arrive after car I. So in this case, if I'm going to look at C sub 2, I want to look at the cars that arrive after car 2 and parked to the left of spot J. So in this case, I look at the cars, I look at where the 2 is. So here's the 2. I look to the left of the 2, identify the numbers that are larger than 2. So in this case, 3, 4, and 5. And then I throw those in the set together with the number 2. That's it. So you do this for every C sub I. So in this case, C sub 2, I identify where the 2 is. I look to the left. I keep track of the numbers that I see that are larger than it. And I put them in the set together with the number 2. So that's C sub I. I'm going to then consider omega sub I or omega sub J. And then what that is going to be the actual indices of where those numbers appeared. So we already knew C sub 2 of pi for this particular pi is 3, 4, 5, 2. I now identify the indices. So 3 appeared at position 1, 4 at position 2, 5 at position 4, and the 2 appeared at position 5. So 1, 2, 4, 5 is this omega. Okay, so having all of that, then here's the result. We couldn't quite give you the equality that we were looking for. We still have this nice product formula, which tells me that the number of preference lists that park in the order pi is at most this product. Now, the nice thing is that we can tell you when the equality happens, and it happens precisely if the permutation pi avoids these two patterns. And so the proof is there's a lot of cases, but this paper is up on arXiv. So let me end, and I'll end early because I love taking questions. So I want to tell you that parking functions are, they have tons of applications. And so, of course, in combinatorics, group theory, discrete geometry, hyperplane arrangements, you see the one in the chat with chip firing games, and computer science. So there's tons and tons of applications. There's even more ways to think about generalizing these concepts. And so I just wanted to share some of them. So of course, there's a wonderful paper where they're parking on trees. So there's basically, the cars, you label all the vertices of a tree, and then cars have a preference for a parking spot, and then they enter along one of the leaves trying to go to that preferred parking spot, and then they exit a root of the tree if they can't park. And so there's been some work on that direction, pun intended. There's also MN parking functions, which are the ones where there's more parking spots potentially than cars. There's also parking sequences, which are super awesome and something that we've been studying now, which is cars having potentially different lengths. And so how do they park without colliding if they're taking more than a single spot? And then there's also something that we worked on, which was called parking completions, where you imagine that overnight there was some construction that occurred and some of the spots are occupied or unavailable. And then the queue of cars comes not knowing that that has happened, which feels very true to life sometimes, given how much construction happens. And then there's also a more general case of the interval parking functions that I talked about, which is subset parking functions. So in this case, just cars have multiple preferences. They don't just have to be in an interval. And so there's tons of open problems that remain. And I think these are really wonderful types of projects to start with students because it's a very low floor entry. You can explain parking functions to anyone. And the ceiling is really high. So there's a lot of really cool techniques that you can use to enumerate all of these objects. And so I also wanted to point out to a paper that I wrote with this group of wonderful individuals on parking functions, choose your own adventure. And so the article is written in the spirit of a 1990s book where you make choices as the reader along the way to create your own kind of parking function research project. And at the end of the article, if you don't want to pursue the adventure, you can go to the end of the article and there's a table with some of the open problems. And then if there is any work that has been done on that particular question, we point you to some of the citations. And so I will end with a terrible parking function found in nature. But also, in case this is of any help, I wanted to put some references there for you and some slides. So I figured tech allows us to take a snapshot and then you can have those links. So thank you so much. I'm happy and eager to get any and all the questions you might have or suggestions for other things we should look at.
Okay. Thank you, Pamela, for your talk, for your nice talk. And we are looking now for questions.
Okay, a question and suggestion. First, a question. What's the reason for calling it Naples parking, Naples functions?
You're trying to get me in trouble, but I will say what I was told. So the student was, like I said, from Fort Myers. So that's where Florida Gulf Coast University is. And when they explained to me what it's like to live in Naples, they said that people do this all the time. That
Naples, Florida, not Naples, Italy, I guess. Yeah.
That is correct. It is Naples, Florida, and that a lot of people are driving down one-way streets and you'll just see them backing up. And so because she came up with it, she got to name it and the name stuck.
That's cute. And now for the suggestion, my former students, Yukin Yao and other people talked about the area statistics of the usual parking functions. So I'd be interesting if you also consider the area statistics for these amazing new classes. Thank you.
Yes, and I should point out, let me see if I can quickly get there. Sorry, I don't have my list out, but the version of the Naples that I showed you, that did consider an area statistic. So of course I might not make it.
Nice. So this could be extended. This recurrence could be extended for the area generating function.
Precisely, yeah. So in this paper right here, in the counting the Naples parking functions through permutation in the Naples area statistic. So that's the paper that.
Right. Okay.
Yeah.
That's great. Thank you.
So we did do it, but only for the Naples. We haven't done it for other versions, and I think there might be something there. So I think you're absolutely right on. That should be a next project.
Okay. Good luck. Thank you. It's very interesting.
Thank you.
Can I add a small comment?
Mm-hmm.
It was a very nice talk, and it's so interesting to see those cool results that result from these alternative considerations of parking functions. So really nice stuff. And just to add to Thomas's comments there from the chat, I had reason to introduce something called tiered parking functions in a paper from 2 years ago, where you have cars of K different colors, and you specify the number of cars of a color less than yours in which you want to park. So just seeing your talk, all these new questions arise about, well, what more can one say about that? So
funny you should mention that, Mark, because the MSRI Up 2021 group, there's a group whose paper we haven't yet finished, but we do have some enumerative formulas for some of your tiered parking functions.
Oh, wow.
Yeah, and I think we have a slightly different definition than what you had. But yes, that's sort of forthcoming. It's in the pipeline. But yeah, I should tell you that there's we've considered this.
That's fantastic. I can't wait to hear the details.
Thanks, yeah, absolutely.
Thanks.
Any other question? Let me see in the chat if some questions. No, just some thanks for her nice presentation. If no other questions, again, we thank you, Pamela.